And thank you, Justin. We're going to move on now. Questions for Justin during the coffee break or after we're done all the talks. But we're going to move on to Frank Russo next, who is a professor at Ryerson University, and he's done so many different things, but amongst them, he has directly engaged with empirical investigations of Gene's work on melody. So, Frank.
Okay, so it is a great pleasure to be asked to participate in this event. My history with these books comes a little bit after their first publication. It was the mid-90s. I was a new graduate student in Lola Cuddy's lab at Queen's, just down the road. And at the time, I had a laundry list of truly crazy ideas that I corresponded with her about prior to my arrival, and I continued to pepper her with these crazy ideas when I arrived. And she was patient. She listened to them, and she slowly brought up some ideas that I might think about. And one day she raised Eugene Narmour's work, and that was one of those. Another one of those watershed moments that happened in Kingston, this one a couple decades after the ones we heard about earlier. While I wouldn't describe the book as an easy read, the insights provided seem profound and well beyond what could be arrived at from the perspective of experimental methods. A short while after having initiated my first experiments with the theory, I recall generated a machine that spit out, it used a Monte Carlo approach, and it spit out melodies that were informed by the principles and with the Krumm-Hansel-Kessler profiles. So I had some data in hand and some ideas about how all this might fit together, and I made the pilgrimage out to Philadelphia to speak to Gene, and he helped me shape some ideas about how what's going on at the surface with respect to expectancy might influence what we hear hierarchically. And I will talk to you a little bit about that today, amongst other things. What I'm going to do is take you through a highly selective and an admittedly self-absorbed review of the nature, effects, and origins of the bottom-up principles of the IR theory as proposed by Gene. I'm not going to discuss all the parameters upon which the IR theory may operate. I leave that to Gene. As we've heard, he's going to take us through the full gamut. I will focus exclusively on the bottom-up aspects explicated by Gene that apply to melody. All right, so as I said, I'm going to begin with a description of the nature of the principles. So the principles were first formalized in work by Glenn Schellenberg and Carol Krumm-Hansel. What you're looking at here is the formalization from Krumm-Hansel in 1995, published in Music Theory Spectrum. You can see that there are 5 principles. I'm sure all of you are familiar with this formalization. We have implication and realization, and what we're capturing as was just mentioned, is both the size of the interval and the direction of the interval. And depending on the size and direction of the interval, we have implications for the size and direction of the interval to follow. A high level of closure, which is another aspect of the bottom-up approach, will generate a weak expectancy for the next note to follow. A low level of closure will generate a strong expectancy. So there were a number of validations of this particular formalization. 3 of them I list there that pertain to corpus studies, that pertain to production studies and perception studies. The question has been raised over the years about whether there is redundancy in the principles, and clearly there is redundancy. Some of the predictions are duplicates. So a number of parsimonious reductions have been provided by Glenn Schellenberg. And you're looking at 2 of them. The conceptual reduction that he first came up with led to the revised formalization on your left. He later completed a principal components analysis of the predictors in the revised, reduced formalization that yielded a very parsimonious, and I'll say simple, two-factor model on the right. Critically, the two-factor model was found to not compromise the model's predictive power in the domains that it was tested. However, it's important to note that while the principles have been tested in a variety of contexts, the surface has only been scratched. And I mean that at multiple levels, I'm afraid. That was not intentional. The surface has only been scratched with respect to the range of contextual possibilities within which the principles may exert their power. So as an analogy, I'll raise depth perception. And you probably weren't expecting to hear about depth perception, but I think it's a useful exercise. There are so how do we see depth? There are numerous cues that are available. They can be broadly split up with respect to monocular, those that can be perceived with one eye, and binocular, those that require two eyes. So we have interposition, the interleaving of objects in space, relative size, texture gradient, motion parallax, aerial perspective, accommodation. On the binocular side, we have stereopsis, convergence, and shadow stereopsis. There are more. These are the ones that are all agreed on. Let me assure you that there is plenty of redundancy in the predictions that can be derived from these mechanisms. Okay, so another way of thinking about this is that they're not redundant, but rather overdetermined. So for example, binocular cues like stereopsis tend to be better in the near field for things that are right up close and in our face. Monocular cues like interposition tend to be better in the far field. As Al Bregman said just the other day, we have many cues available for streaming. Their utility can only be revealed in particular circumstances. Similarly, differences may emerge when it comes to the bottom-up principles of the IR model. To date, the range of music that has been assessed it's been subjected to is relatively narrow. So I think this is an important point. In some respects, I feel that the takeaway from the bottom-up aspect of the theory is prematurely narrow and not willing to appreciate this perspective of overdeterminacy, which Eugene himself has advocated. All right, so I'm going to switch gears a little bit now and talk about context effects on the predictions. So as I mentioned, there are predictions regarding the size and the direction of intervals. So we know that intervallic perception is not defined by way of fundamental frequency differences or pitch distances alone. There are many factors that can influence the size of an implicative interval. Among them, we can look at register effects, and we can look at multidimensional interactions and multimodal interactions. All of this data has been percolating over the last 20 years, and I think that this data could be used to inform and extend some of the predictions in the IR model. So just a very quick overview. We know that there are register effects on the perceived size of intervals. So if we take the same interval and we put it in the high pitch register, its magnitude seems much larger than it does in a lower pitch register. And this is particularly the case for ascending intervals. And there are many possibilities for why this is, and we explicate some of them in this particular paper. But one of them is that it has something to do with an embodied physical constraint. And the one that makes the most sense for me here is a vocal constraint. Okay, it's simply more effortful to extend the same pitch distance in higher pitch registers. Timbre. We know that there are interactions between timbre and interval size. So we can take an ascending interval and have the first note of that interval be a dull timbre or a bright timbre, and the combination of timbre and size will influence, again, the magnitude of the size perceived. So as a very quick demonstration, I'm going to play you a incongruent pairing of spectral brightness and pitch direction, and then I'll play you a congruent pairing. And I think you'll appreciate that the magnitude of interval size is different in the two cases. Okay, there are many things going on. I haven't calibrated them in this room. There were loudness differences. But even if we got rid of those loudness differences, there's certainly some bleed from the spectral attributes of those tones influencing our subjective size of the interval. So you can imagine how that might shape the implicative nature of a given interval. Okay, and just to show you what the data looks like here, I'm showing you 7 semitones for some reason on the left. This just occurred to me earlier today, and 6 semitones on the right. And what I'm highlighting here is the incongruent presentation of the larger interval and the congruent presentation of the smaller interval. And you see that we actually have a reversal, so there's an illusion in this case. There are also many visual influences that Bill Thompson alluded to in his talk. So in this particular study, we did many things, but in this particular graph, we took intervals, we took perfect fifths and major sixths, and we paired them with incongruent visual recordings. We never used the perfect fifth recording. What we did is we took a large interval visual recording, like an octave, or we took a small interval recording, like a major second, and we paired them with the intervals. Okay? And as you can see, when we have that visual skip, we have a kind of lengthening of the interval. So you can imagine how live performances of music might again shape the implicative nature of a given interval. So next I'll turn to effects, and I kind of regret describing it as effects, and I've got something that looks like special effects, but so what I'm referring to is how can we use these principles in a manner that helps us to understand some of the superordinate aspects of perception of melody. Okay, so one possibility is emotion, and Eugene talks about emotion, and Lenny Meyer before him certainly talked a lot about emotion. The notion that's presented is that interruption of parametric expectation generates some sort of arousal boost, which in turn may be ascribed to an emotion. And this seems entirely plausible, and I know that Eugene thinks that this is one of the reasons that we're particularly attracted to vocal music, that it disambiguates and allows us to ascribe meaning to those moments of arousal boost. I don't think, however, that we can account for all emotion through the lens of the IR model. I'm sure I'll be corrected, but from my perspective, the theory works well for high arousal emotions where there's an arousal boost. I don't really see its effectiveness in explaining low arousal emotions. There are some connotations that low pitch offer on their own without getting into an implicative interval, but I don't think that that's powerful enough to really describe some of the low intensity emotions that we experience in music. I think we really need some sort of an embodied perspective to understand those aspects of emotion in music. But ultimately, more research is needed there, and I won't say much more about that. So another thing that you can do is use the principles to understand melodic similarity. So there's been a lot of work that's been done in music informatics over the years to look at similarity. A few researchers, there's some of us in my lab are involved in this as well, have taken a more cognitive approach to understanding similarity. And people that have taken a more cognitive approach have found utility in use of the principles. So prediction of similarity between melodies is improved by incorporating melodic expectancy as assessed by the IR model. So you take you take tonality and various low-level aspects of melody, you add in melodic expectancy, and you've explained more variance. Naresh Vempala and I have been doing similar work. We're looking at, rather than differences between melodies, we're looking at melodic variations. And again, we find an improvement by incorporating a measure of melodic contour that's ultimately derived from the IR model. And this is going to be presented in the poster session later today. Emergent structure. So in addition to understanding expectancies from note to note, we can look at expectancies on a global level. And you can imagine that if you continue to fulfill expectancy at a surface level and a global level, you have the opportunity for cohesion in a melody. So we looked at this in, Lola Cuddy and I looked at this in a number of experiments. I'm providing a schematic here so as to not concretize this into any particular notation. Ultimately, it's the size and direction of the intervals that matter. We've done this in an atonal context, we've done this in a tonal context, and we get similar results. So essentially what we've done is we set up a regular violation of expectancy at some periodic interval. So in this case, we have a ternary kind of structure that's instantiated by having a denial of expectancy between the implicative interval formed by the second and third tone and the realized interval formed by the third and fourth tone. And what we get is the fourth tone emerging to an emergent level. We get the same thing happening at the seventh tone. We can then look at what happens when you have a process or a continuation of small interval size intervals in the same direction at the emergent level, or when you have some sort of change in contour at the emergent level. In these experiments, all our stimuli were isochronous, very boring melodies, I'm afraid. All melodies were tonally ambiguous, and all melodies had identical pitch range and mean interval size. So we really sucked the life out of these melodies, and we did so really to be sure that what we were manipulating was the emergent and surface level structure. We used two basic paradigms. One of them was a serial reconstruction paradigm that was borrowed from Deliège and colleagues. So in this case, we take a melody and we divide it into a puzzle of 5 pieces. We scramble the puzzle, and as a participant, you are to recombine the pieces so that they form the whole. This is what serial reconstruction accuracy looks like when we have manipulated the emergent level and the surface level. So the melodies that are easiest to reconstruct are melodies that are simple at the surface level and simple at the emergent level. Those that are hardest to reconstruct are melodies that are complex at both the surface and emergent level. These are very small effects, but they're real. We get stronger effects when we get people to make a cohesion rating. So we simply ask them to listen to the entire melody and evaluate how cohesive the melody appears to be. And I'm showing you the same pattern here. I won't say too much more about this other than to say that we went to great lengths to control other possible explanations, and we also manipulated the extent of recursion in the melodies. So in some experiments, we had a high level of recursion early on that reinforced the ternary or binary structure we had. In other cases, we had a very small amount of recursion. And we still, in either case, we still see those effects of emergent level structure. So I'm going to move on now to the climax, if you like, and talk about, it's always fun to talk about origins. So origins of these principles. So we have many places to look. Of course, Narmour claimed in 1990, his view may have changed, that the bottom-up principles are innate in some capacity. So how did this come to be? Perhaps we have perceptual primitives that have come to us through our evolutionary history. Certainly evolutionary pressures have led to auditory scene analysis, and there is some overlap between those that model and some of the principles here. But I would argue that some of the origins can be found in embodied sources. So not necessarily those that are found in the environment, but those that are found in the manner in which our own bodies and voices move through space. And I think there's plenty of opportunity for evolution in that capacity as well, and I'll speak to that a little more in a moment. Associative learning is another way in which these principles have been explained. Brett Arden did a thesis with David Huron, and he found that the distribution of events was a determining factor in explaining expectancy. Pearce and Wiggins have done a very good job with their n-gram computational model. The model yields powerful results that account for bottom-up and top-down aspects of the IR model. And they've extended this model in various ways. But I'll remind the audience that I feel comfortable saying this because we are engaged in computational modeling in my own lab, and I often wonder what is it that we're really modeling. My point here is that just because a computational model works, it doesn't mean that it has biological plausibility. Okay, it's just one way that this solution can work. Other possibilities, physical constraints. We had a great paper by Paul von Hippel and David Huron, a series of papers, but what they argued is that it was the effect of tessitura that influenced the tendency for reversal following a large leap. Okay, so this tendency, this registral direction principle, or gap fill as Lenny Meyer had it, it was the product of tessitura somehow. And the really convincing evidence there, I think, is that median departing skips are more likely to lead to reversals than median crossing leaps. Okay, so again, median crossing leaps are less likely to be followed by reversals than those that are departing from the median. So there's some logic into, if you go too high, you've hit your head and you've run out of space, regardless of what instrument you're playing. Another possibility, though, is embodied constraints. And Zotar Etienne has done a lot of work looking at movement imagery, and he might talk about that in just a little bit. Vocal motor constraints is another idea that's been raised. So Glenn Schellenberg raised this idea in '97 very briefly in one line of his discussion. We explicated it a little independently in 1999, and I've come back to this hypothesis in various ways over the years. There have been proposals about the role of the action observation system, or the mirror neuron system. So this is a highly controversial network in the brain, popular yet controversial. The reason it's controversial is that we don't know that there are mirror neurons, but there's clearly some system of simulating actions that we have. A number of theorists and empiricists have proposed that this might play a role in our perception of music. There has been, finally, some empirical evidence. There's a scattering of papers for involvement of the MNS. And I'm showing you data here from a recently published paper from our group where we used song stimuli, and we showed that there is more mu desynchronization, which is a marker of MNS activation during perception of song as compared to perception of control stimuli. And I won't get too far into the details. I only have 5 minutes. I want to get a little further into this hypothesis. So the motor constraints hypothesis that we first raised in 1999, we explicated it a little bit. Adam Tierney and Annie Patel and I did in this paper. What we did is we looked at cross-cultural regularities in song, and we had a very large corpus study, song from around the world, and we found that the melodic arch, the tendency for a melodic arch, was present within birdsong, but not at the phrase level. It's present in the note level. And the thing you need to know about birds is that they breathe between every note. We tend to breathe between phrases, they tend to breathe within every note. So the constraint here is that breath is necessary, and there is an end product of this melodic arc. I could explicate that further. Final note lengthening is another thing that we see in both bird and human song that can be explained by motor constraints. Pitch proximity, though, is different between birds and humans. If you look at bird song, you can show that they tend to have more leaps at the end of the day than do human singers. And the issue is that they have a double set of vocal cords. So you can imagine that you could be tightening up one set and relaxing another, and you can imagine the flexibility that affords. So again, you can use a motor constraint approach to understand the differences that you see between species. This is an example. I'm going to keep going. No, I don't have enough time. So the last common ancestor, there's similarities between birds and human song, but the last common ancestor between birds and humans is more than 250 million years ago. So we share as much in common with the dinosaurs as we do birds. So thus, any similarities in the patterns of song production are likely best understood as a result of convergent evolution. Okay, there are certain biomechanical constraints that impose themselves on bird song that we share, others that we don't share, and that leads to a different pattern of song and expectation. Paulo Amarante, a postdoc in my lab, and I have recently extended this work, and we've been looking at the prevalence of pitch proximity in vocal and instrumental melodies. And the idea here, essentially, is that there's a vocal template that perhaps we carry forward into listening to all music. But it should particularly present itself in the context of vocal melodies. And you can see the vocal melodies in the blue bars. This is a corpus analysis, and the instrumental classical themes in red. And there's clearly a difference. When we look at an individual piece, like Bach's B minor Mass, again, we see a difference. Instrumental solos involve less pitch proximity than do the vocal parts. So the constraints are more complicated than just, it's hard to sing big intervals. There's also what can be referred to as the modal voice, so the most comfortable singing range. So this is old music education data from Moore, and what he had is children and adults sing songs spontaneously, and he was interested in where they would sing these songs. And you can see that they don't tend to sing them at the top of their range, they don't tend to sing them at the bottom of their range. It's about a third of the way up. Okay, so let's say 4 or 5 semitones from the bottom of the range is a comfortable place to be starting that melody. So if this is the case, then we might expect more skips where we're more comfortable singing, right? And we have found support for that. So we call it the low skip bias. So again, we looked at the same corpus analysis, vocal and instrumental melodies, and across what you're looking at on the x-axis is the quintile of the pitch range, so low to high. And you can see that there are more skips in the lower quintiles and fewer in the higher. This is particularly the case in vocal melodies, but it's there all the way through, which is some support for this vocal template idea. There could be cultural associations wrapped up in this as well. Paulo did a very clever thing here. He decided to look at the frequency with which composers are involved in vocal music. And what we were able to do is plot a correlation between the percentage of vocal output and the percentage of skips that these composers use. So I think that the vocal constraints based on this may have imposed themselves through associative learning, through practice, through the fact that our very first experiment with music is our voice. we babble or sing before we are going any further. Those are all good candidate possibilities. And there's also 250 million years worth of evolutionary potential within which some of this might have been ingrained in our auditory templates as well. To conclude, I would caution the adoption of parsimonious formalizations of the IR model. We have not tested this model in diverse contexts. There are context effects that will influence implications. The IR principles can be used to explain similarity, memory, and cohesion in melodies. And finally, biomechanical constraints, especially vocal motor constraints, may underlie at least some of these principles. Thank you.